Alright guys, so I was just revising my binary trees notes. So these notes are just collection of every bit of learning that I have learned about binary trees and more. But let's see. So what is a binary tree? A binary tree is a hierarchical data structure. Binary means every node has either 0 or 1 children. So this node has either uh, like 0, 1 or at most 2 children, right? So these is 2 children, this is 1 children, these guys are no children, right? And like this is called the root. And then the concept of leaf. Then there's an internal node. So what is an internal node? So internal node is a one which has at least one child. That is an internal node. And there is of course terminology like B is parent of D and E, B, C, D, F are children of A, right? These all are children of A. A is an ancestor of B, C, D, F. Height of a tree is usually defined like number of edges from that node to the farthest leaf, right, to the deepest leaf. So if there was some more node here, this height would have been 3 of this A, and height of the tree is actually height of the root. That's important. Then how many types of binary trees are there? So this is important. Now one of like this terminology can be loose. Some people use different terminologies, but first we have full binary tree. So full binary tree means every node has either 0 or 2 children, right? So here every node is either 0 or 2 children, so that's a full binary tree. Okay, so what is the use case of this? These are used for like Huffman coding and segment trees, if you know, whatever. So then complete. So what is a complete binary tree, or like sometimes also called almost complete binary tree? So these are, you can say, what forms the binary heaps. So all levels full except the last level, and in the last level all nodes have to be as left as possible, right? So the filling strategy is like this. So once you're completely done with the level, then and only then you start with another level. Another level also you fill from left to right. Then what is a perfect binary tree? Every internal node has degree 2. So this is, I guess, you can say binary tree with as much nodes as possible, right? So all leaves are at the same level, right? So even if you observe here how many nodes are there, so here there are 2 levels and nodes are 3. Here there are I guess 3 levels and nodes are what, 1 plus 2 3 4 5 6 7. So here I guess the total number of nodes are 2 power n minus 1, right? So where n is the number of levels you have. Then you have degenerate tree. So degenerate tree is sort of a path only. So every internal node has a degree 1. Pathological tree, fine. Then you have a balance tree. The balance tree is one in which the height of the tree is order of log n. That's a balance tree. So these are used for like AVL trees and all. Now this is usually the constructor implementation of C++. So if you are asked in an interview, this is how the tree node should look. At least in case of C++, should be a struct in data tree node, like it will have pointers, right? So a node will point to both of its children, right? So this I'm talking specifically about lead code cell interviews, not for competitive programming, because in competitive programming everything is a graph, right? So data left, right, and these are the constructors. So first constructor simply does nothing, it just initialize a node straight away. So data is 0, left is null, right is null. So it simply like this node with 0, and this guy has nothing, this guy has nothing. Then another one is with the data. So data is x. So data is x, left is nothing, right is nothing. Then it does take left and right both. So left and right both. So it means x. It will take left. It will take right. Right. So that's how it is. Yeah, left and right are pointers, by the way, right? So pointers to the tree node. Right. Okay, fine. Then this is a Java version. Fine. And then tree traversals. These are the most important ones. Pre-order, in order, post-order, and they call it pre-order because here the root of a tree or a subtree is visited once first. In means root is visited after left and right. Post means root is visited. In means root is visited before left and right. Post means root is visited after left and right. Okay, and they're pretty straightforward in recursion way. Like of course, in tree traversals mainly we have two ways: BFS and DFS. Both are used. Okay, both are equally important. So yeah, but we are used to more DFS versions, right? Anyway, so pre-order, uh, the way you should think about this is like if you are given a tree and you want to figure out the traversal for it. For a node, you can assume that for every node, you can assume when we are here it for the first time. Then when we are here it for the second time, and when we are here, we are the third time. So if you print the node when you are here, it's pre-order. If you print the node when you are here, it's in order, and when you print the node when you are here, it's actually post-order. Okay. So here, if you observe here, go from top to bottom, left to right, print when visiting first time. So first time means directly A, B, D, B, D, E, C, F, right? So A, B, D, C, F. And you can observe here, root, left, right. Then in order, right? So first time visited, not printed, first time visited, not printed, first time visited, not printed, second time printed. So D, B, D, A. Then first time visited, not printed, second time visited, C, F, right? So you can observe left, root, right. Print when visiting second time. Similarly here, first time visit not printed, first time, second, third time. D is printed. Then again B is printed. Sorry, B is not printed. E is printed. Then B is printed. Then again A is not printed. C is not printed. Then F is printed. C and A. Right. So left, right, root. Cool. So implementations like recursion wise are pretty straightforward, right? For pre-order, what do we do? Of course, if root is not equal to null pointer, the way it works is first print root, then left, and then right. Similarly, for in order, it will be for left, root, right. Okay. For post order, left, right, root. Okay. Of course, this is the base condition. Now, some people also write it separately. If root is equal to null pointer, then simply return, and then fine. So, the interesting one will be the iterative versions. Now let's look at the BFS version. So it's sort of a level order traversal in case of trees. This has to be done using queues, right? So there are many two implementations of this. People directly ask you, you can say print them level by level, like A, B, C, D, E, F. Or sometimes people might ask you what are the nodes in level 1, what are nodes in level 2, so on and so forth. So both can be implemented very easily. Anyway, so we want to innovate traverse level by level. So we'll use queue here. And for storing output array of array, fine. Then it's pretty simple. You initialize a queue, you initialize your answer, then if of course tree is null, then you return fine. And then otherwise push the root guy, and while queue is not empty, you want to store all the level nodes. So first figure out the level size. Now go through all the nodes in this level size. All the nodes level size, take that node out, if this guy has a left child, push it. If this guy has a right child, push it, and pop it from the queue. So maybe you could have popped it here as well. So you could have popped it here as well. That would also work. So no issues, right? And then you can just store for level nodes of I equals to node.data, right? Cool. So this is again assuming that we have storage available, but fine. So this is just a pseudocode, okay? So this can be easily implemented. Anyway, and then to the answer we add all the level nodes and print answer. Now interesting questions, iterative version of pre-order. So these are important questions in case of interviews. Let's see. Okay. Anyway, iterative pre-order. So instead of recursion stack, we want to use an external stack. So what is pre-order? Pre-order means A, B, C, right? First A, then B, then C. So how are you gonna do it? So whenever you are a node, you wanna first print that guy, right? Then so then the next guy you want to print is B, and the next guy you want to print is C. Okay. So how are you gonna do it? Let's see. So firstly, so we'll use external stack for obvious reasons. Okay. A, B, and C. So whenever I'm A, first print A, then go to its left child, right? Go to its left child, but before that, push its right child, right? Because we will have to come back to its right child afterwards. So maintain a stack. We will go through its left child, but also push the right child first, and then push the left child. Then we are going to visit the left child. Again, we're going to do the same thing. Push the right child of B, and then visit it. So if you want to see here, okay. So if root is null, return fine. So empty tree. Otherwise, maintain a stack. Push the root guy. Okay. So push the root guy, then take it out, print it. Then I want to go to its left, fine. Before that, push C, because now there is no recursion, right? So we're not gonna come back to this. So push right first, push right first, okay? Then push the left guy. Cool. So eventually, what will happen is when you have this, let's say this left guy, when you visit a guy and you push first right into the stack and left into the stack, you're effectively what you're doing is you're doing root left right. Cool. So that's one thing. Cool. So you can verify this for yourself. Then what are you gonna do for iterative in order then? So iterative pre-order was pretty straightforward, but iterative in order will be interesting. So in order, what you want to do, go as left as possible, and then you want to print the root, right? So you don't print the root straight away. You first go as left as possible. So here you go as left as possible, then print D, right? Then after you have print the D, you go to right, and then again as left as possible, but there is no left, so then print F. Then go right, and again as left as possible, but there is no left, so again print G. Then go right, go as left as possible, but there's no left, so G. Right? So this is how our logic should look like. Go as left, print the root, right, left, print the root, right, so on and so forth, right? So in the answer, you have to store the in order traversal. Fine. So we'll need a stack here. Then root is equal to null, then return answer. So if the tree is empty, you do that. Otherwise, store the root. So we are gonna as left as possible, right? So that's what we're gonna do. So node equals to root. So while true, go as left as possible, right? Go left as possible. So while going left, push. Okay, because when you come back, this will be printed first, then this will be printed, so on and so forth, right? Cool. Okay. So while node not equals to null, you push the node. So go left. So node equals node left. And now when node has become null, eventually now you know the top guy has to be printed. If stack is empty, break, fine, the traversal is complete. Otherwise, the top guy has to be printed. Okay. So this okay, print this guy. Then go right, again left. Okay. After let's say you have printed this, you come back here. You print this, go right, but there is no right here. So right. So node equals to t dot right. So if it is null, then it's fine, right? So node equals to t dot right. Go right if it makes sense. Now, if you observe here, yeah, go right if it makes sense. Cool.